Okay, so welcome everyone to the last talk of the program. So it's my pleasure to introduce Karen Yeats. Karen is a professor at Waterloo and holds the Canada Research Chair in Combinatorics and Quantum Field Theory. In 2003, as an undergrad at Waterloo, Karen was the runner-up for the very prestigious Morgan Prize, which is given every year to an undergraduate in Canada, the US, and Mexico. Karen received their PhD in 2008 from Boston University, was a previously professor at SFU, and is the author of 2 books. Today, we're going to hear about combinatorially controlled resurgent series, so please take it away.
All right, thank you very much, Steve. Thank you to the organizers as a whole for inviting me. And as you know, I'm not exactly from your community, but I hope that these will be things that you will find interesting. So I work on combinatorial problems in quantum field theory, especially, and recently also a bit in quantum gravity. And what I'm going to tell you about today is about some resurgent series or some divergent series that we can do some interesting stuff with, that part of the advance was to see some better combinatorial control of them. Okay, so just briefly say something. Of course, you're maybe not too surprised when you start to see some interesting generating functions in physics. I know some of you folks do things that are at least closely enough related to problems from statistical mechanics that you probably at least are conversant with the sort of language people use. And you know, of course, that really when people are talking about things like partition functions, they're kind of just talking about generating functions, right? And so it's not too surprising to find interesting series that are indexed by combinatorial objects in physics. And furthermore, in quantum field theory specifically, we typically expect our perturbative expansions, these divergent series, or these series that we encounter, we typically expect that they should be divergent. And that's partly just you try to understand them, and in practice this seems to be true. That's partly because they're indexed by Feynman diagrams, by classes of graphs, and those grow pretty badly, so you expect some divergence just from there. And also there's a physical argument due to Dyson from the 50s, which said, well, if the series actually had a non-zero radius of convergence around the origin, then as well as the part over here with positive coupling constant that we kind of like, there'd also be some part on the other side with negative coupling constant, and then you'd get a lot of interesting problems like charges attracting and other things like that really physically are not a good idea. So you don't expect convergent series. Okay. Let me just draw a cartoon of what a scattering experiment might look like, because the kind of physics I do is well, I mean, you know, there's like physicists, and then there's like the theoretical, and then the mathematical physicists, and then there's like actual mathematicians. So I'm all the way over here. But if you go over here a little bit, these are the people who do high energy physics or the physics of particle accelerators. And so what you imagine in your cartoon of your scattering experiment is that you've got some particles coming in, and you've got some coming out, and you don't really know what happens in the middle. There's just some sort of giant explosion that you know, something happened in there. You know what came in because you know you made the accelerator and you prepared the beams, and so you know what's in them. And you know what came out because you have detectors, and that found all the things. But you don't know what happened in the middle. And if you want to take this perturbative approach, then you want to sum up over all the possibilities for what happened in the middle. So, you know, for one simple little thing, maybe you're interested in something like this, where there's an electron, it's going to split into, there's a photon, and it's going to split into an electron-positron pair, and you want to think about all the ways that something like that could happen. So maybe they just exchanged a virtual photon in there, maybe some other thing happened, maybe something like that happened. Maybe this happened, etc. So this is a little piece of quantum electrodynamics, which is the theory of photons and electrons, and so the quantum theory of electromagnetism. Anyway, divergent series. There's an awful lot of graphs. That thing is not going to converge. But despite the fact that they're divergent series, they're often pretty useful. So we don't want to just take a completely pure math perspective and say, well, that's only information about the germ of the function, and there's just nothing else there, and too bad, because they're clearly a lot more useful than that. If you have your friends at CERN who are doing these particle accelerator experiments, they actually want you to compute the amplitudes of these various diagrams, and they will use that in their experiments, or use that to, in evaluating the outputs of these experiments. So, they actually compute things at finite coupling, not just the germ. Additionally, you want to understand non-perturbative effects. So these often go under the name of instantons. So you expect, for physical reasons, that there's going to be stuff going on that's asymptotically flat at the origin, so that you really would not see it in a perturbative expansion. Some of it can be stuff that comes sort of for topological reasons, if you will, and others maybe in other ways, but physically you expect it to be there. And these are these non-perturbative effects. And so again, strictly speaking, if I think of this divergent series as just telling me about this germ of the function at 0, then it can't possibly tell me about that. But again, in practice, you say, well, actually, I can try to do some resummation. I can try to understand something. And if things are sufficiently mathematically nice, then I should be able to get some information about the non-perturbative effects out as well. And so that's what we want to do. And that's what physicists want to do. Okay, so what are some things? For a long time, physicists have used resummation techniques, Borel resummation, various more powerful generalizations of it, things like that. People also want to understand what's going on with these instantons. So you have instanton expansions, and those basically fall into this world of transseries that people studied from other directions. That both people more from the analysis side and also more from the logic side have studied. And then there's also this idea of alien calculus, or of resurgence. Another way of alien calculus is a way of trying to, again, maybe think about things like Borel resummation in a more, dare I say, algebraic way. And this idea that these different things all talk to each other, which is all I'm going to say about what resurgence is. Okay, and this all works especially nicely when there's a differential equation to drive it all. And so what I'm going to tell you about is some cases like that. All right, I am going to start with one example. This starts with something, so this is mostly about I'm going to tell you about an example that Michael Berinsky and Gerald Dunn studied. But we're going to start something a little bit earlier. Broadhurst and Kreimer in the 90s, in the late 90s, they looked at certain diagrams that show up just in a special piece of a massless Yukawa theory. So I'm just going to draw a picture of the diagrams that we'd be looking at. So we're looking at what happens when we have one little bubble graph like that, and we're going to insert it into itself in all possible ways. So, I could put it inside itself one time. I could put it inside itself more times. And you guys are sitting there and you're saying, wait a second. I know what these are. What are they? Just plain rooted trees, right? I just inserted this little bubble into itself. I can chain them up. I can make rainbows of them. But really what's going on here is there's a little tree structure, right? Rooted tree structure. Yeah? Okay, good. But this is a class of diagrams you might care about. I'm pretty sure that that David Broadhurst and Dirk Kreimer studied it because they could. But I was once, back in 2014 or so, when I was still at SFU, I was at a physics colloquium, and some guy from condensed matter came, and he had exactly the equation that defines those things, and he wanted to talk about it, so that was good. So now I see you wrote that down, but of course they don't actually care about pictures of graphs, right? What they actually have is this equation defining, you want the amplitude of this, and so you have a recursive equation that defines that amplitude, and that's what they studied. They studied it basically by pure cleverness, very David Broadhurst approach to everything. I don't know if anyone in this community knows him, but he's definitely up there on the cleverness side of things. And he found a solution. They found a solution, involved the error function. And along the way, and the part that's going to be most useful for us, is that they found a nice differential equation for the anomalous dimension. Okay, so what the heck's the anomalous dimension? In fact, the whole rest of the talk is going to be about anomalous dimension. So maybe you would like some sort of vague physical hand waviness about what the heck an anomalous dimension is. So the idea, you want to think about dimension in the sense of a scaling dimension. And in a classical situation, you would expect your scaling dimension to be like maybe an integer, right? Something like that, constant, at least. But in the quantum situation, what's the anomalous all about? Well, it's not. It doesn't behave as nicely as that. And so you get something that's going to be a function of your coupling. And I'm going to always use gamma for my anomalous dimension, and I'm going to use X for my coupling, which I realize is a weird choice. I started making that choice because I also very much want to think of my coupling as my counting variable in a generating series. And so I guess in this community, people like to use Z for that, but I happen to tend to like to use X for that one. So anyway, the other way you could think about it is if you think about the Green's function, giving this amplitude, then in these sort of cases, that's going to be a function basically of two variables, the coupling and some thing that's the external momentum, or maybe just the overall energy is probably the best way to think about it. And if you think of it as a series in the coupling and the log of the energy, then this is really just the linear coefficient of energy, of log energy. Anyway, it's a thing. Physicists care about it. And it's going to be really nice for us to deal with. So it turns out there's the little differential equation for it that Dirk and David found back in the late 90s. Okay, and that's nice. And you can maybe expand it out. And I don't know, again, I don't know if you guys are looking at that and you're saying, wait, do you know what that is? Turn off the physics. You say, oh, there's all that physics and I did not understand it. So you have to take that hat right off and throw it away and just put on your pure combinatorics, pure enumeration hat. With your pure enumeration hat. Anyone see what that is? What that's the generating series for? I should have written another term. If I'd written another term, you might have been able to guess a little more easily.
Would the next term be 4 to the 4th?
Oh, no, sorry. I really should have put another term. They're rooted connected chord diagrams, it turns out. And this is actually one of the classic recurrences for it, because one of the ways you can understand a rooted connected chord diagram, I'm not going to talk a lot about rooted connected chord diagrams, so I'm not going to give you some precise definitions, but just for concrete sake, there's an example of a rooted connected chord diagram. Because they're rooted, I might as well draw them on a line instead of on a circle, but of course you're welcome to just put them on a circle instead. And they're connected in the obvious sense. If you want to formalize that, you can make the intersection graph of the chords, and then that graph should be connected. Anyway, this is actually one of the most classic recurrences for them, because if I want to make a rooted connected chord diagram, then somewhere in a rooted connected chord diagram, I'm going to choose an insertion place. And what am I going to put into that insertion place? I'm going to put in another rooted connected chord diagram. And that is exactly this recurrence. So if I use the same color coding here for a moment, I had to pick an insertion place. So I didn't quite use the same color coding. So I'm picking an insertion place. That was picking this insertion place. What am I picking an insertion place in? I'm picking an insertion place in a rooted connected chord diagram. And what am I putting in the insertion place? I'm putting a rooted connected chord diagram. And there's a base case, because yeah, good to have a base case. All right. This recurrence will come back. Okay, what do I do with it? Well, they now we're on to what Berdinsky and Dunn did. What did they do? They said, okay, this is a really nice little differential equation. It's just the sort that if you're in this resurgent community, so you go talk to someone like Ovidio Constant or something like that, and you say, okay, yeah, that's the kind of thing I want to analyze it. I can try to understand it. And they did this in two different ways. I'm going to start over on this side. One approach is to say, well, instead of looking for a series expansion solution to this, that's just a series expansion in X, let's put in some sort of trans-series ansatz, which we can also think of as our instanton expansion. And here, what we want, so we put in this other parameter sigma, and our sigma is supposed to be like this part that's going to be asymptotically flat around the origin. So it's going to be, we wanted this sigma in the end to be something like an e to the minus 1 over x kind of thing. And you do, in fact, see that e to the minus 1 over x showing up down here, a little lower on the page. And so then what happens, we'll just plug that in, plug it into the differential equation. And if I take the coefficient of sigma to 0, well, I clearly just get the original differential equation back where I'm trying to now solve it, get a series solution in x. So that's just the whole, that's just the original question, just back to the where I was before. But I could also take the coefficient of sigma to the 1, and I get some other differential equation that's going to involve the solution to the first one and my new thing, my C1. And it turns out in this particular case, this one's nice enough that you can solve it. And there's an expression for it. And you see the kind of things that you expect. You see this e to the negative 1 over x. So that's your sort of instanton piece of it. And, you know, some stuff's going on. You see the gamma, because the gamma was the solution. That's the C0, right? Gamma equals C0. And the point is you can solve it. Okay, but another thing you could do is you could say, look, that solution, that first one, the gamma, is it's a divergent series, and you can understand exactly how bad the divergence is. Okay, and that little part I think I got to change the color of, because I really don't think anyone can read this. So this is this idea of alien calculus. Maybe I'll just make it black for now, but I might switch it back later. So what is the idea here? If I have some series here, and suppose I know that the coefficients have some asymptotic expansion where I know exactly what the gamma. So I need a gamma of n plus beta. So I need to know exactly what the shift in the gamma is. And I need to know exactly what this exponential factor here at the, or this like something to the n factor here at the front is. And then I have an expansion in the subsequent corrections, right? That's how you do that sort of thing. You've got some asymptotic expansion, and that's what you expected asymptotic expansion, sort of shape and asymptotic expansion would have. And then we're just going to define this curly A to be let's just make the series out of the coefficients of that expansion. Okay? And I'm going to just put that back to the way it was before. And so now let's do that in this particular case. And there's a machine to do it. In this particular situation, it's nice enough that you can get a nice closed form for it. So you apply it in this case. In this case, the alpha has to be 2 because this thing is growing like a 2 to the n with plus this gamma, 2 to the n times the gamma of, and the n is n plus a half. Sorry, I didn't say that very well. This thing is growing like gamma n plus a half, 2 to the n. And so those are your parameters for your A, and you just plug this into the machine, and the machine tells you something like that. And then these are actually the same, up to some normalization and some chord diagram identities. I realize they don't look exactly the same right now, but there are various, there are identities of chord diagrams, including this one up here, that you move between those. And so those are basically the same thing. And so whether I'm interested in the series given by the coefficients of the asymptotic expansion, or whether I'm interested in taking an instanton expansion and putting that in my original differential equation, I'm getting basically the same answer out. And that's the magic of resurgence. And this case, which I don't want to spend more time on, is even prettier, because in this case, you can keep going, right? You say, well, this series, that's, also divergent. You can also figure out what the asymptotics looks like. And so you can do it again, right? And you can keep doing it. And so they, in fact, get an all-order solution. And there's been some other similar cases that have been studied by various subsets of the people here. So Michael Brinsky and David Broadhurst studied a slightly different example. Borinsky Dunn and Max Manig studied another one that's going to come up briefly later. Various other combinations of these people looked at versions of this. Although this first one, which really remember is just about rooted connected chord diagrams, ended up being the most beautiful one. Okay. All right. Well, I would like to do something that's related to that, but that's both more combinatorial. Because notice there were chord diagrams, but we didn't really use them other than that they gave us a nice interpretation for the differential equation. But we didn't do anything combinatorial with them. And the other thing is, I'd like to have something that's a little more systematic, at least in the sense of giving us a nice family, like a playground of sources of examples, rather than just being like, well, some people in the 90s studied this because it came from this particular physical example, and this other thing came from this particular physical example, and we could make a toy, but what sort of systematically a story that we could do. And that's what I want to tell you about today. But I need to go on a little bit of a digression to do this, to tell you about something else that I've been doing for many years, which is solving Dyson-Schwinger equations using combinatorial techniques. And previously, I'd been doing it mostly by, surprise, surprise, rooted connected chord diagrams. But more recently, and this is the version I want to tell you today, because it's going to be the one that's going to tie nicely to the last part of this, using what we call binary tubings of rooted trees. Okay, so you can think of this as a tool to calculate this anomalous dimension. You actually can calculate the whole Green's function, but we're going to stick to the anomalous dimension today because it's a little bit simpler. Okay, what do I mean by this? What is a binary tubing of a rooted tree? So I'm actually not going to write down a definition for you. I'm going to give you an example, because it's one of these things that's very clear when you see an example. So, it does not need to be a binary tree, though. Let's make a non-binary tree just to make it totally clear. That's not what the word binary, that's not where the word binary goes. The word binary goes with the tubing. So what is a binary tubing of a rooted tree? Well, the whole tree is a tube. And now, where's the binary? I always want to, whenever I have a tube that has at least two vertices in it, I want to split it into exactly two tubes. So for instance, I could split this one here. And then I could say split this one here. And then I could say split this one here. And then I could regret that my tree has so many vertices. Okay, so that is a binary tubing of a rooted tree. Not a particularly exciting object, but they're quite useful. If you are the sort of person who plays with or has seen this sort of tubing, why are they called tubings? Who's thought about graph tubings? These are not exactly the same as graph tubing. So the sort of tubing used to build the graph associahedron, these basically differ by the line graph. So if you take the line graph, then in a natural way, you can think about which edges the tube enclosed. That gives you a tube on the line graph. And those then become literally the tubings you would use in the tree case of the graph associahedron. These are also closely related to the poset tubings, which are a more recent invention. So they're a special case of those. Anyway, whatever, they're a thing. They're a combinatorial object. So you could count them, perhaps with interesting parameters. And basically, that's what I want to do to give you an expression for the anomalous dimension. And what's my input going to be? So my input is going to be some simple tree class. So that means some trees where the generating series for the class of trees is just made by composition with some other series. And that's going to be the one that's going to describe the insertion structure of the Feynman diagrams. So if we went all the way back here, notice we had a very simple tree class here, one of the simplest ones of all, because this one, my simple tree class would look something like this. Right? Why did I put that X there? Not here. Because it's just a sequence of trees. It's the kind of tree where you just have a sequence of trees as your children. Okay, simple tree class. Oh, and what do I mean by describing the insertion structure of the Feynman diagrams? I mean exactly what we saw right in this picture, right? They say I inserted this little guy into this other guy, and that's inserted into the big guy, and that's how this is made, right? So that's what that's all about. Okay, you need one other piece of information, which I want you to think of as just given to you by the physics. This is the place where the actual Feynman integrals, I've been glossing over the Feynman integrals, right? But as we said, the physicists don't actually care about pictures of graphs. They don't actually care about counting graphs, not exactly, because each graph needs to be weighted by its Feynman integral. That's its actual contribution to the amplitude or to the thing that you're trying to compute at CERN. But fortunately, I don't need that information for each graph. That would, otherwise there'd be nothing left. It's good enough just to have it for the one diagram that was being inserted into itself with one additional extra piece of information. I need to regularize, and specifically I need to regularize by taking the edge that I'm inserting into, and so the Feynman integral is some integral, and it's got a factor for each edge, and the factor for that edge I want to raise to the power 1 plus rho. And so I get some sort of function of rho. And if anyone's actually an expert, I also want to set the external moment to some fixed value. Anyway, so then the only thing it's still a function of is that rho that I raise that power, that edge to. And so I have some function, I'm going to call it f of rho. It turns out, sort of for scaling reasons, that it'll always have a simple pole in the cases that we care about. And so I just want to think about the Laurent expansion. And so from the point of view, if we're just saying, let's play some pure combinatorics, let's suppose some physicist came in and asked us to solve this problem for us. And we said, I don't want to know anything about physics. I just want to know what are the inputs that I need. Your inputs are the simple tree class and this Mellon transform as an expansion. So these FNs, you just imagine, they came out of the integral. You don't know what they are, but your friend who calculates integrals can tell you maybe what they are. Okay? And if you have that information, I can tell you what the anomalous dimension is. And there it is down there. The anomalous dimension, you have to sum over the trees from your simple tree class. So if you can enumerate them, you could replace, you could replace this by whatever whatever your generating series of them. The size of t here is just the number of vertices in the tree, x to the size of t. And now you have to sum over all the tubings, all those binary tubings of those trees. And what do you do? So yeah, don't worry about reading the tiny print. I'm going to do the example, and you'll see what's going on. Is I want to make a monomial of these f's for each tubing of the tree. So let's use this tubing of this tree, except let's not, because that tubing of that tree has gotten really messy. So let's just redraw that one a little bit better, and then it'll be less messy. So I had a big tube. The problem is I didn't make my tubes big enough, so they got kind of jammed up. Okay, and I had this tube, and then inside that tube I had that tube. So there, now it's not as bad. So here's what we're going to need, so that you can, because I didn't even tell you what the rank is, so you have to look at the picture because I didn't tell you. First, I want to mark at each step. I want to mark the upper tube. So inside this first tube, one of the tubes is on top and one of them's not, right? Just from the root structure. One of them contains the root and one of them does not contain the root. So let's take the one that contains the root and we'll mark it. That's an upper tube. Okay. Now we'll go inside the next guy and we'll say, okay, one of those contains the root and one of them doesn't. So let's mark the one that contains the root. Right, now we'll go in there and the next one, well, one of them contains the root and one of them doesn't. So, and similarly inside this little tiny one, as well. Okay, and now here's what I want to do. So this is much easier than looking at the formula, because all I want to do is for each vertex, I want to count how many upper tubes are rooted there. So for the root here, there's 2 upper tubes that are rooted there. So I'm going to get an F2. For this guy down here, it's a leaf. So no upper tubes are rooted there. So I'm going to get an F0. For the root of that sort of first subtree that we made there, well, 1, 2, 3 upper tubes were rooted there. So that one's going to give me an F3. Well, all the rest of them are leaves. So all the leaves are not, it's just a bunch of F0s. Okay, but why did I write it that way? That's a silly way to write it. All right, that's the contribution of that tubing. Oh, yes, good point. Thank you. Right. So that's don't look at the formula, just look at. Okay. So that's a combinatorial way to compute the anomalous dimension for any physical process that you can build in this sort of recursive way by inserting. And in fact, you can do it quite a lot more generally than this. We can do systems, we can do multiple primitives, we can do multiple insertion places that are distinguished within the primitives. There's a whole story here that's not today's story. Make sense? Or at least you're like, well, I don't know why, but it's like a thing. Okay. Now I want to put these two things together. So if we go back to the original Yukawa example, so we'd already noticed, I'd already said, well, that's just plane trees, right? We'd already noticed there were plane trees. We'd already written down the equation for plane trees as a simple tree class. But it's also true that the Mellon transform is really easy in this case. And there it is. It's just 1 over rho 1 minus rho. Okay, about the simple polar, I was like, yeah, just don't worry about it, right? So, right, we indexed, did you notice how I indexed the things? They were off by 1. So, you know, I really just multiplied it by rho. So it's just 1 over 1 minus rho. So the coefficients are all just 1, right? All the FIs are 1. Okay, that's pretty simple. Notice I'm actually slightly cheating. Because if you actually literally write down the Feynman integral and regularize it the way I described, you actually get that. But I already took out the extra powers of 2 because clearly there's just going to be a power of 2 that's going to scale with the size, right? So I can just, but I already scaled out the power of 2 for you. So you don't have to worry about that. Well, and that's why that case was so simple. That because the f of rho, the sort of the part where the actual integral showed up was kind of trivial in that case, and otherwise it was just plane trees. Okay, so if you look back, what did I tell you here? I said here I told you could calculate the anomalous dimension by summing over the tubings of whatever class of trees, taking this monomial. That monomial is now always just 1 in this particular case. So now I'm saying you can calculate the anomalous dimension by summing over the tubings of all the plane trees. But we already noticed something about that, right? That's here. We also noticed this also counts, it's also just the generating series for rooted connected core diagrams. So if you're bored, one of the consequences of this says that tubings of plane trees are in bijection with rooted connected core diagrams. And so if you're bored, you can think about that.
Is this number not the double factorial?
No. So if you don't have connected, then the number of rooted core diagrams is double factorial. But if to put in the connectivity condition, you lose that.
Steve equation, I understand that n should be even.
N is the number of chords. So, right, it's, yeah. Yes, exactly. There's a particular class of connected core diagrams that are in bijection with all rooted core diagrams of size 1 lower, and so are counted by double factorial. They're the ones that in my language have exactly 1 terminal chord, and that class actually ends up being really important in this larger story, but I wasn't going to go into detail about that today. But if you write out the first few examples, you will see that it fairly quickly is not double factorial. Anyway, so if you're bored, you can work on that. You can work on that bijection. I suggest finding the recursive one first, because you can find a decomposition that has that same differential equation we had up there. Okay, well, remember I mentioned how there are a bunch of papers by various subsets of these people, and one of them studied this version. So this is actually a phi cubed example for anyone who knows their physics. It's a particular scalar field theory that's a useful toy model that shows up quite a lot. Not actually in the standard model, for instance, so not actually at CERN, but that's in some ways the simplest example of a quantum field theory. And so it's something that's studied a lot as a toy model. Here it's the same T of X, so we're still just working with rooted plane trees. And the f of rho has changed, but it still has sort of this nice property that you know, it's just 1 over a polynomial and the polynomial factors into really nice factors. And so, well, we decided to look at that case in general. Okay, and I don't actually want to deal with the roots. I want to deal with the inverse roots. So, but obviously you could just scale yourself between them. Scale between these. Because I want it to look like this. So we're going to look at the story of taking what works in general for any class of trees and any Mellon transform, and in fact, much more generally than I wrote down. And we're going to look at the case where we're in the plane trees. We're looking at plane trees. And when we're looking at a Mellon transform that looks like this, it's just 1 over a polynomial. And actually, I'd like these a's for now to give it a nice combinatorial interpretation to be integers. So I've got integer inverse roots. Of course, if I've got rational ones, I can just scale away some denominators until it all works out. So we can say rational, polynomial with rational roots. Okay. And again, you got to put on your classic enumeration hat. You're teaching your first enumeration course. What is that the generating series for? If the a's are integers. Oh, get rid of that initial row. I don't care about that anymore. What does 1 over 1 minus a row count? Lots of things. What's your favorite thing that it counts? What does what's your favorite thing whose generating series is now I guess I'll call it an x, where a is an integer, a is a positive integer. Yeah, I like that one. That's my favorite one too. So let's use that one. Lots of other things too, but let's use that one. And so if I put them together, what is this? This is just the generating series for words on, you know, some big annoying alphabet. Right, but they better be disjoint. Okay, but now with the property that, like, really it's a Cartesian product, right? So it's really like, okay, all the omega I letters have to come before all the omega j letters if I comes before j, right? Right. So easy, right? I mean, it's kind of a stupid thing. Why do you want to count that? But it's clear what it is, right? I better make my I not look like a J though, or otherwise it will not be very good. It's a thing. Okay. Now, what were we interested in? For the f of rho, what do we do with it? We said we're going to expand it out. We're going to let the coefficients be these little f's. And then what were we going to do with them in our equation up here? If that was that thing I said, don't look at that because it's really small. But we did it in the example. What did we do? We took out 1f for each vertex. Okay. So I need to take out one of these for one thing here for every vertex. Okay, and then what was it doing for the vertex? What was rank? Rank here was the number of tubes that were rooted there, the number of upper tubes that were rooted there. So this number is supposed to be the number of words that of that length that have some property, and that's associated to the number of tubes, of upper tubes that are rooted there. So I can just put letters on the tubes, on the upper tubes, right? So to get to that, what do we want to do? I want to put letters on upper tubes. Okay, but then I have to have this annoying, like all the whatever letters come before all the other letters. What's that going to mean in this case? Well, if I'm looking at all the upper tubes that are around a particular vertex, so here's a vertex, it's got some upper tubes. The upper tubes, they all have to be nested, right? Because every point you cut something, there was some more tree, you cut something, there was some more tree. So the upper tubes always are that are rooted at the same vertex are always going to be nested. So they have a linear structure. So I just translate that condition over, but now instead of coming before, they come on tubes that are inside the other tubes, right? So with the nesting structure of tubes with the same root being the linear word structure. Okay, so there, in case you can't read what I wrote, you can see it. Here it is. So we're counting tubings where the upper tubes are labeled by letters from that alphabet, and where the tubes with the same, 4 tubes with the same root, letters from the earlier alphabet come inside letters from the later piece of the alphabet. That's all. Again, you're like, well, you know what? If I was just, out there looking for the most beautiful things to count, that would not be the first thing that comes to mind. But okay, it's not so difficult. And you know what? Physics told us to count that. Okay, but there's something even better that's good about these. Because now, notice the anomalous dimension is now literally the generating function for those, right? There's no other weights, just that's that. And in order to do this sort of resurgent analysis, we wanted a nice way to understand the anomalous dimension. And in particular, it's really nice to have a differential equation, because then we can do that instanton expansion thing. And it also puts us in a really good position to do the alien calculus, like whichever of those approaches that you like, having a nice differential equation or a nice system of differential equations. That's exactly what you want as input. And okay, not too surprisingly, I've got some reasonable object. This is probably something that if you think about it, if you, again, say, well, someone told me to enumerate this, how do I do that? You're going to find some nice decomposition. And it maybe won't surprise you too much that the decomposition is going to give you a differential equation, system of differential equations. So let's do it. We need to think about a little bit of a picture. Okay, give a system of differential equations. I'm going to do an example right here. It does, of course, it's not too bad in general, but we'll do an example. So what example are we going to do? I want to do basically this f of rho, the one that's up here, but I want to already have done the little bit of scaling. So if you just invert all of these, of course, you're going to get a 6, 3, 2, right? The 1, 3, 2, 3 turns into a 6, 3, 2. So let's look at this example. So we've got 1 minus 2 rho, 1 minus 3 rho, 1 minus 6 rho. Okay, that's kind of nice. And now, what was this condition? So if we think about how do we make a tubing? What's the outermost thing? So there's the outermost tube, and inside the outermost tube, it's broken into two subtubes. One of them is an upper tube. So this one's good, upper tube. And the other one is going to be the lower tube. It's going to be broken somewhere, and then there's going to be the lower tube here, or it's going to connect it somewhere. Okay. And now, in terms of this condition about tubes with the same root, the only thing that's really going to matter. So say I'm making one of these. I haven't done this yet. So right now, I'm here. And I want to put these two things together. Okay, but notice that's not an upper tube anymore, because the outermost tube wasn't an upper tube. So what's going to happen when I put these together? I have to pick an insertion place somewhere, some edge, to insert the one tree into the other tree. And now that I've put this on here, this guy has turned into an upper tube. And the condition about the words, the only thing that matters is when there's upper tubes that are rooted at the same vertex. So whatever's going on with the upper tubes in here, don't care. It's all the same as ever. The only thing that's going to matter is the upper tubes that are rooted here at the root of this guy, which is the root of the whole tree. Okay, so this suggests how we should do our decomposition. We should split our gamma. Okay, well, there's some sort of base case. And then after that base case, I want to split it into what was the label of the root. So I've got 3 alphabets. I've got omega 1, 2, 3 in this particular case. So I'm just going to call them L1, L2, and L3 for whether that outermost tube around the root had its letter from which alphabet. Okay. And well, okay, now I have to think about which way around. I'm not sure if I've done this the right way around. So if it's, okay, what do we want to do? This part, the part we insert, is always just any old thing. So that's always just gamma. And now we have to count how many insertion places there are. Well, if you think about it for a moment, here's a tree. How many insertion places? 1, 2, 3, 4, 5, 6, 7, 8, 9. If you think about it for a little while, you will see it's twice the number versus -1. So 2x d by dx -1. And now what do I apply that to? Well, I got to apply it to this upper guy. Okay. And so, well, when is stuff the most constrained? If the outer guy is going to have a label from the first alphabet, then it's really constrained because it had to already be from the first alphabet. And then the only thing left to do is I have the size of that alphabet number of ways to choose that extra label, right? So I didn't leave enough space. That was kind of silly of me. Slide this over, and I just get a 2 here. And so on. The other alphabet had size 3. If you're in the second alphabet up, you could have anything from the first alphabet. Oh, or you could have just X. Sorry, that's also a mistake. So this should say X plus L of X, L1 of X, and this is X plus L2 of X, X plus L1 of X plus L2 of X. Okay, and then I'm done. You're like, oh, I don't want to see you write this. That was an exercise, right? Just completely an exercise. And what did you get? You got a nice system of differential equations. Each equation is linear. They have this extremely structured triangular structure. So it's like everything you could possibly dream of when you're trying to do your analysis. So it's just the right form to do this analysis. And also the meaning of some special cases is really apparent. So I'll say just a few words about those things. So let's do the analysis first, because I actually wrote some of it down. I'm just going to do an example because I'm sure you really only want to see some examples right now. So let's think about 2 alphabets. And then there's kind of 2 different situations. There's the situation if both alphabets are the same size, or if the 2 alphabets are not the same size. And so you can say one of the most interesting questions is what is the instanton? What is the order of the instanton, if you want to think about it? So the part you maybe want to care the most about is sort of this part. Like, what is the, you know it's got to be some sort of e to the -1 over x-ish thing. It's got to be something flat at the origin, telling you what the instanton is. So, and if you went back to that thing where you plug in some trans series ansatz and you take out the different coefficients, that's the story we're doing right now. And we're saying, okay, what's the first term of each term in the instanton expansion, or each independent piece in the instanton expansion? And so when the AIs are different, you get exactly what you expect. You get 1 over 1 minus x's, and you have sort of 1 for each scale that's involved in your problem. That's what you expect. Totally textbook. Great. Now, when A1 equals A2, then you go and you open up the textbook that all these analysts wrote, and they're like, well, in the generic case, blah, blah happens. And you're like, but I'm not in the generic case anymore because they're equal. But you still need 2, sort of like when you're, solving linear systems or whatever, right? And what you end up getting is this 1 over root x behavior. Which, okay, well, I'm not actually a resurgent person. As you may have guessed, I'm actually a combinatorics person and somewhat a physicist, but not really. Oh, that yellow highlight is no good at all. Okay, we're going to re-highlight that in orange. I highlighted this and no one could tell. And now I'm highlighting this. And hopefully now you can tell. Much better. Okay. I'm not actually a resurgent person myself, but the people who are tell me that these 1 over root x's are quite surprising. And so this is already demonstrating itself as being a really interesting playground where some unexpected behaviors are showing up in a situation that's just very controlled. And every single step of the way, we had some combinatorial meaning to the various pieces. And so on this side of the story, the sort of things that we would want to investigate next are things like when logs show up. So in general, when you have some trend series, it's not good enough to just have your powers of x and your powers of e to the 1 over 1 minus x. E to the minus 1 over x. Sorry, that's what I meant. You also end up having some log terms. And when they show up is at this point still kind of mysterious. And so here we have a nice playground where we can investigate when they do or don't show up. This is related to this idea of resonance. The intuition that the physicists have here is that if these A's, or possibly if the inverses of the A's are in nice ratios, then that's when things should simplify. That's what's known as resonance. But that's more of an intuition than a theorem. And so this is, again, a nice playground where we might be able to get some rigorous theorems in that direction. And I think this is also just an encouragement to the mathematicians working in these areas to try to think of some, to recognize that it's really important to look at the non-generic situations. Because that has been one of the impediments to formal results so far, is that when you just open the textbook, the theorems are often not in the cases that we need them. Okay. Another thing that I think is very interesting, and here I'm not going to write this annoying thing again. I'm going to copy it so that you don't have to put up with that. So again, in some of those other papers in the literature, people looked at various special cases. But it was a little bit mysterious why the special cases behave the way they do. And the fact that we've been able to pull apart the combinatorial setup so that we're just really literally counting something means that we can see these things a lot more simply. So what is this rainbow case? If you go back to the original Yukawa example, I mean, I just want graphs like that, or if you think about the trees, I just want chains. They're called rainbows because the graphs kind of look like rainbow. Now you say, well, but that's a chain. What, you said something else is chain. What's chain? So this side, what people are thinking of as chains here is, okay, well, I always had to have that one outer one, but after that, I just want a little chain of bubbles in here, like this. These are related to what in the physics community are known as renormalon chains. And there's a certain amount of controversy in the community about whether renormalons are telling you an important part about what's going on in terms of the divergence or not. So it's good to investigate them. And I call them, I also would maybe call these corollas because the graph is just this little fan. The corolla. Okay. All right. Now the point is I can just immediately read these off. So, okay, so that's a little bit too big now, it doesn't fit. Oh, whatever, you know what the end of it says. Okay, well, if we're doing the rainbow, what's going to change? Well, there's only ever one insertion place, right? I just always insert at the bottom. So this whole thing, that's just gone. I don't even need that anymore. Because I can just erase it. It's gone. Gone. Okay. Too bad, that's gone too. What else happens? Well, did I forget something? Maybe that's all that happens right now. Leave that for a moment. I think we're good there. We just got rid of that part. So, okay, it's not even a differential equation anymore. It's much simpler. Of course, it's going to be much simpler. What happens for the chains and the corollas? Or chains or corollas? Well, here, what you're inserting is now much simpler, right? You're not inserting an arbitrary tree. You're just inserting a leaf. So this gamma in the front here, these are going to go away. and they're just going to turn into X. So now what's gone funny? Oh, well, good thing we're almost at the end because something weird happened. Okay. So these are just going to turn into X. And now if you think about it, the number of insertion places is about half what it used to be, right? Because if you think of sort of all the insertion places would be like here, 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 right? But I can only use the ones that are at the root. So there's actually only now a linear number of insertion places. Just X. There's N. There's just that many insertion places. Okay. And you're good. So you can really understand exactly what's going on in these special cases just combinatorially, and that you immediately see what's going on, what sort of equations you get. And then the flip side of that is you tell this to your colleagues and they say, oh, but I want an example that has, that still has the gamma and it has just this x d by dx instead of the 2x d by dx minus 1. And you're like, okay, I can immediately tell you what that's going to count, because that's saying I'm inserting arbitrary trees, but I'm only inserting into the odd indexed or even indexed, however you want to think about it, insertion places. And so you get, you just read off exactly what it means. So when your colleagues say, oh, I want to study this particular special case, you just read off exactly what it means. And then you have the same combinatorial control they had over all the rest of it. So that's basically my conclusion, which is that you've got yourself into a situation where you have control over all the pieces and you're in the right part of the picture to be able to do this sort of resurgent analysis. And that gives you what I hope you would agree is a very pretty playground. And in the end, it's actually telling you something about particle physics.
Okay, questions?
I have one to